technique, basic instrumentation and working, separation theory, and question and answer session. So the first question is, why chromatography? Why it was required to develop a chromatography? So just have a look at this pictorial representation here. One of the manager in one of the food product company, he is asking one of the laboratory scientist in his company that I need a quantitative separation of some of the carbohydrates which are present in our product. Okay. And the scientist thinks that if I need to quantify each of the carbohydrates which are present in the product separately, I have to separate them. Then and then only I can quantify them precisely and accurately. Okay. So that's how chromatography plays a very critical role. Okay. So who invented chromatography? So there was one Russian scientist called as Mikhail Svet. He was a botanist. Okay. So he invented chromatography in 1903. So since he was a botanist, he wanted to do a separation of some of the colorful plant pigments using, so he used a column of calcium carbonate for separation of different plant pigments which were present in the plant extract. The word chromatography has been derived from the two Greek words basically, wherein chroma means color and graphy means a graphical representation of the data. Since then, chromatography is developed and is used as an invaluable tool in laboratories for separation, identification, and quantification of different compounds. So, what is chromatography? It is a technique which is used for separation of individual compounds in a given complex mixture. Okay, it is used for qualitative analysis as well as quantitative analysis. Now there are different types of chromatography which have been developed over the number of years, such as paper chromatography, column chromatography, ion exchange chromatography, gel permeation chromatography, often called as size exclusion chromatography, supercritical fluid chromatography, gas chromatography, TLC, and high performance liquid chromatography. Okay, so out of these, gas chromatography, high performance liquid chromatography, these are the most modernized techniques in the chromatographic world. Okay. Hello. Am I audible? Can somebody just confirm?
Yes. Yes.
Okay.
Yes.
Yeah. Thank you. Thanks for confirmation. Yeah. So in today's presentation, we are going to focus more on the high performance liquid chromatography. Okay. So what is the use of HPLC, that is high performance or high pressure liquid chromatography? So using HPLC, you can do a qualitative analysis, that is you can find out what are the components A, B, C which are present in the sample, and you can also do a quantitative analysis. Okay, that is you can find out what is the concentration of the compounds A, B, C which are present in the sample. Okay, that means you can do an identification as well as quantification of those compounds. Okay. Chromatography has wide range of applications. It can be used in pharmaceutical analysis for quantification of the drugs from the drug products, biopharmaceutical analysis, food analysis, petrochemical analysis, chemical and agrochemical analysis, clinical research, forensic sciences. So it has n number of applications in the laboratories. Okay. Now, what is the basic principle of HPLC? It is a type of liquid chromatography which is used to separate the compounds that are dissolved in solution. Okay, so this is very important that the compound has to be dissolved or fully dissolved in the solution. Then and then only it can be identified or quantified with the help of liquid chromatography. Okay. It consists of a solvent reservoir, often called as mobile phase, a pump, sample injector, liquid chromatographic column, often called as stationary phase, and a detector. Chromatography involves interaction of analytes with the stationary phase, which travels along with the mobile phase. The analytes which are traveling through the stationary phase, so those analytes basically retain on the stationary phase depending on the certain physicochemical properties of the analytes. Okay. Those analytes which are retained on the stationary phase then further elute out with the help of suitable mobile phase. Okay. And finally, you get a plot of analyte response on the y-axis against the retention time, since the basic phenomenon is the retention of the analyte. So on the x-axis, you get the retention times of the individual compounds. So these are some of the basic terminologies which are often used in chromatography or high performance liquid chromatography. So the first is mobile phase. So it is basically a solvent system which carries a mixture of samples to be separated to the stationary phase. Okay, what is stationary phase? So as the name suggests, it is something which is stationary, that is not moving, correct? So it is immobilized surface which is particulate in nature, and this is the region wherein the compounds in the samples get separated. It is often called as liquid chromatography column. Okay. Next is retention time. So it is the total time an analyte spends on the column or stationary phase after it has been injected. So the retention time basically depends on the interaction of analyte and the stationary phase. So the more a time takes to elute from the stationary phase, higher will be the retention time. And finally, chromatogram. So it is basically the signal or output of the separated components by the chromatograph. Okay, so you get a response graph of response against retention time. This is just the basic schematic of the high performance liquid chromatography. So on the right hand side is the Waters Equity UPLC H class system, which we have in the Bombay Veterinary College LCMS lab. Okay. So first you need a solvent reservoir or mobile phase system, then followed by a pump which basically pumps out the mobile phase which we store in the solvent reservoir, then a sample introducer or sample injector, often called as auto sampler, then the stationary phase, that is the HPLC column, detector, and the computing system. Okay. So what is the role of the pump? So as I've told you, it is used to force or pump out the liquid mobile phase through the chromatographic system at a defined flow rate, generally expressed in ml per minute. Okay. So basically there are two types of pumps, binary solvent manager and quaternary solvent manager. So the difference is in binary solvent manager, you can make use of two different solvent lines, whereas with the help of quaternary solvent manager, at a time you can make use of 4 different solvent lines. That's why it is called as quaternary solvent manager. Okay. Uh, Pump can be operated in two modes, isocratic mode and gradient elution. Okay. So isocratic mode is basically wherein you keep a fixed composition of the solvents. Suppose you have water in solvent line A and some organic solvent in solvent line B, and if you keep a fixed composition of 70:30, so that 70:30 composition will be flown through the system at a given runtime. Okay. Whereas in case of gradient elution, you can vary the composition of the solvents over a period of time. Okay. So that is the difference between isocratic and gradient elution. Next is sample manager, often called as auto sampler. So it introduces the sample into the mobile phase. So it basically has an injector, and the samples have been stored into the HPLC or UPLC vials. Okay. So injector basically takes this sample from the sample vials, and it introduces it into the mobile phase. Okay. The next is stationary phase or the column. So this is a very critical component as it is responsible for the separation of compounds which are present in the given sample. And finally, the detector. So it detects individual analyte that is eluting out of the column based on their interaction with the stationary phase, and it provides output or signal to the data system, which results in the chromatographic plot. Okay, so there are different detectors which can be clubbed or can be used with HPLC or UPLC systems. So I have mentioned some of the detectors such as ultraviolet or photodiode array detectors, fluorescence detector, ELSD detectors, RI detectors, electrochemical detectors. So different compounds, as they will have a different physicochemical properties, they will require different detectors to be seen. Correct. For example, if some of your compounds has chromophoric properties, then they can be detected using UV or PDA detectors. If some of the compounds has fluorescence properties, then you have to use fluorescence detector in order to detect and identify and quantify them. So similarly, different detectors can be employed for quantification of different compounds. But out of these, mass spectrometer provides a very significant advantage as compared to the other detectors which are present because of the way it functions. Okay, so we are going to discuss about the mass spectrometer in the later session. Okay, so in chromatography or in HPLC, the separation is basically based upon the differential migration of analyte between the stationary phase and mobile phase. Okay, so this is just a small animation. Okay, so this is a schematic of the HPLC, wherein you have solvent reservoir or mobile phase systems kept at the bottom. Then you have pump. Then there is one mixer which basically mixes the two different solvents which are coming from the two different solvents lines before it reaches to the injector. Then you have an injector which basically introduces the sample into the mobile phase. Then the mobile phase carries the sample which have been injected to the stationary phase or the column, wherein the chromatographic separation takes place, and the separated components then individually moves to the detector. Okay, so just look at this animation. So the compounds have been separated, and each individual compound is moving to the detector, and the detected compounds have been eluted, and it is displaying in the chromatogram. So there are two types of chromatographic modes generally. First is normal phase chromatography, and the other one is reverse phase chromatography. Now, what is the difference between normal phase and reverse phase? Okay, so in normal phase chromatography, stationary phase is polar and mobile phase is comparatively non-polar. Okay, whereas in reverse phase chromatography, as the name suggests, it is reverse to that of normal phase chromatography. That means the stationary phase is comparatively non-polar and mobile phase is polar. Okay, so in reverse phase chromatography, it is exactly opposite to that of normal phase chromatography. Now we'll look into the separation theory of liquid chromatography. So what is the retention mechanism? Okay. Now, as a new chromatography user, we often get this question that how different compounds elutes at different retention times. Like for example, here in this particular graph, there are four components A, B, C, and D. Then we often get a question why only compound D is highly retained and it is eluting after A, B, C, and why only compound A is eluting at the first. Okay, so it basically depends on the different retention behavior of the compounds. So how does it work? So the basic phenomenon in chromatography is like attracts like. Okay, so suppose if your surface is polar in nature, then it will attract the more polar compounds from the sample. Correct. Now let's take a look at this car. Okay, now as we know, water is polar in nature. So the rainwater is falling off on the surface of the car. and this surface of the car is not waxed. So that's why this surface is also polar in nature. So if you can see here in this picture, the water is the rainwater is falling off on the surface of the water, and it is accumulating all over the car. Okay, but so the which represents that it is liking or it is attracting the polar nature of the rainwater. Okay, but in the next picture, if you see, when the surface of the car is waxed, that surface basically becomes non-polar. Okay, so all the rainwater which is falling off and it is polar in nature, now it is forming water beds, and it is disliking the non-polar nature of the car surface, and it is dropping off from the car surface. Okay, so this is how chromatography works. Okay, so the basic phenomenon is like attracts like. That means polar surface will attract polar compounds more, and non-polar surface will attract non-polar compounds more. Okay, so in reverse phase chromatography, the retention mechanism is polarity, wherein, as I've told you, stationary phase would be non-polar and mobile phase would be polar. uh, So in case of non-polar analytes in reverse phase chromatography, those non-polar analytes will be most attracted to the non-polar stationary phase. Okay, as in reverse phase chromatography, stationary phase is comparatively non-polar, and it is less attracted to the polar mobile phase. Okay, and hence for non-polar analytes, you would see a more retention on the reverse phase column. Okay, whereas in case of polar analytes in the sample, they would be more attracted to the polar mobile phase and less attracted to the non-polar stationary phase, and hence they will have a less retention on the reverse phase column. So the final outcome would be, in case of reverse phase, polar analytes will elute out before the non-polar analytes, as they will have a lesser retention on the stationary phase. Okay, now suppose there are three different compounds which are represented in yellow, red and blue in color. So as, and this is consider this as a reverse phase column, a non-polar column, basically C18 column. So yellow, being a very polar or highly polar compound, it likes the polar mobile phase, moves the fastest and comes out first from the column. Red, being moderately polar, it somewhat likes the stationary phase. It will show some interaction with the stationary phase, and hence it will elute after the yellow compound. And blue, being highly non-polar as compared to red and yellow, it will like the non-polar stationary phase surface of the column, and it will slow down. It will have more retention on the column's stationary phase surface, and it will elute out last. Okay. The next is normal phase chromatography. Uh, Again, the retention mechanism is polarity. In normal phase chromatography, stationary phase is polar, that is, it is hydrophilic in nature. For example, silica, and mobile phase is non-polar. Okay, so that would be hydrophobic in nature. So the example of the mobile phase which you can use is hexane. Okay, so again, in case of polar analytes, when you analyze them on the normal phase chromatography, it would be more attracted to the polar stationary phase. Okay, and it will be less attracted to the non-polar mobile phase, and hence it will show more retention on the normal phase column. Similarly, for non-polar analytes, it will be exactly opposite. It will show, they will be more attracted to the non-polar mobile phase and less attracted to the polar stationary phase, and hence they will have less retention on the normal phase column. Okay, so the final outcome in case of normal phase chromatography would be non-polar analytes comes out first or elutes out first before the polar analytes. Okay, so that is the basic difference between normal phase and reverse phase chromatography. Okay, now if you remember the earlier slide, the picture was exactly reversed, right? The yellow compound was eluting out first, followed by red, and the blue compound was eluting out at the last. But in case of normal phase chromatography, now since stationary phase is polar, the blue compound is eluting out first since it is highly non-polar, followed by red since it is moderately polar, followed by uh, yellow compound as it is highly polar. So it will show a maximum retention on the polar stationary phase, and it will show and it will elute out at the end. Okay, so this is just the representation. So basically there are two types of different columns which can be used, basically represented as C18 and C8 column. So out of which C18 is more hydrophobic as compared to C8 columns, as it has more number of carbon atoms and long chain of alkyl groups which are immobilized with the fused silica. Okay, so if you need more retention, you can use C18 columns for the separations. Okay. Now, generally, if you see in the labs, reverse phase chromatography is most generally or widely used as compared to normal phase chromatography. So why it is so? So reverse phase chromatography works on more non-polar or hydrophobic stationary phase, which works well for separation of most of the organic compounds. This means that water or aqueous based solvents can be used along with uh, less polar solvents like ACN or acetonitrile or methanol for improved chromatographic performances. Gradient separations in normal phase are a bit complicated and difficult as compared to reverse phase chromatography. So, and also, since the normal phase chromatographic solvents are more costly or expensive as compared to the other organic solvents which are used in reverse phase chromatography. So reverse phase chromatography is quite easy to operate and also cost effective. Okay. Now, UPLC, that is ultra performance liquid chromatography, is the modernized version of high performance liquid chromatography. Okay, so the instrument which is there in the PVC LCMS lab is UPLC, that is ultra performance liquid chromatography. So this is just the comparison chart of HPLC versus UPLC. So UPLC offers some advantages over the conventional HPLC systems. So the basic difference is the particle size of the stationary phase. So in HPLC, the particle size of the columns which are being used is somewhere in the range of 3 to 5 micrometer, whereas in UPLC, the particle size of the stationary phase which is used is less than 2 micrometer. Okay. Uh, that's where it provides a very high performance over high performance liquid chromatography. The next is column length. Now since for HPLC the column length would be somewhere between 15 centimeter to 25 centimeter, whereas in case of UPLC, as the particle size is less, the column length can be reduced, and hence if the for UPLC 5 centimeter or even 10 centimeter columns can be used, which basically helps in lowering down the total runtime of the analysis. Okay. Back pressure. Now, as HPLC columns have a slightly higher particle size, the system generates very low back pressure of somewhere around 5000 psi. So it has a limit of 5000 psi back pressure, whereas in case of UPLC, since particle size of the columns is less, it generates a quite high back pressure, and hence the maximum back pressure limit of for UPLC systems is 15,000 psi. Okay. Injection volume. So generally, if you see the HPLC methods, the injection volume would be significantly high. So it would be somewhere around 20 to 30 microliters. Whereas in case of UPLC, the injection volume is very less. So you can inject even 2 microliters of the samples and you can get a good response for the compounds. Okay, so if you are working on UPLC and if your sample size is less, so that would not be a problem in case of UPLC since the injection volume is less. and it will consume a very less amount of sample for the analysis. Again, analysis time. Now, as the particle size is less and the column length is less, uh, the total runtime or analysis time in case of UPLC is lesser as compared to HPLC. Okay, because in case of HPLC, the length of column is higher as compared to UPLC. Then sample throughput. Now, as the analysis time drops or decreases in the UPLC, the sample throughput for UPLC would be higher. Correct? Less time for analysis, higher will be the sample throughput. Okay, so it is inversely proportional. Flow rate and solvent consumption. So generally, HPLC systems works on the slightly higher flow rates, ranging from 1 ml per minute to 2 ml per minute. Whereas in case of UPLC, it operates at very lower flow rates, starting from, let's say, 0.2 ml per minute. So it results in a very lower consumption of solvents. Okay, sensitivity. Again, since the particle size of the column is less, uh, the chromatographic peaks are quite sharp in case of UPLC, and hence you get a very high sensitivity for UPLC as compared to high performance liquid chromatography. So this is the basic difference in the features of HPLC against UPLC. So that's it about chromatography. Uh, if anybody has any questions, you can ask the questions if you want. Yeah, so basically, the column selection will be based on the physical chemical properties of the molecules, basically the pK values of the molecules which are present in the sample. Oh no, it basically depends on the separation which you are getting between the compounds. So you have to accordingly select. Matrix, yes, but it will be more dependent on the separation of the analytes, because matrix effect will come later, but separation of analytes is important before considering the matrix effect. If online participants has any questions, they can ask the question. Okay, great. So we'll move on to the next topic. Okay. So till now we have discussed about a chromatography, which is a separation technique, which is used for separation of different compounds present in the given sample. Now we are going to discuss or focus more on the detection part, that is mass spectrometry. Okay. So the outline of the presentation is we will discuss just a basic introduction to mass spectrometry, some of the basic terminologies which are involved in mass spectrometer, uh, MS instrumentation, main ionization techniques in MS, different modes of operation, and finally questions and answers. Okay. So mass spectrometer is basically a very versatile technique, and it, as I have told you earlier, it offers very significant advantages over other detectors because the way it functions. So the mass spectrometers can be used in pharmaceutical industries for reaction monitoring, purification, characterization, quantification of different impurities which are present at trace levels in the drug products and so on. It can be used in biopharmaceutical industries for identification and quantification of different proteins and peptides, so basically large molecules. It can also be used in food and environmental analysis for determination of different pesticides and other elements which are present in the samples. Again, it can be used in chemical industries, health sciences, and so on. Okay. So what is mass spectrometry? So mass spectrometer is an analytical instrument that measures molecular weight or masses of the molecules. So mass spectrometer measures the masses of individual molecules which have been converted into gas phase ions by the process of ionization. Now in mass spectrometer, in order to identify any particular molecule, first it has to be get converted into gas phase ions by the process of ionization. Okay, then and then only it can be detected in mass spectrometer. If the compound is not able, or if the compound is not getting ionized in mass spectrometer, then mass spectrometer will not be able to identify that particular compound. So ionization of the molecules is very, very critical in mass spectrometer. Okay. Now what is ionization basically in chemistry? So ionization, as we all know, it is when a particular molecule or compound acquires either a net positive charge or net negative charge. So that process is called as ionization. Okay. When a particular compound gains either a positive charge or a negative charge, that process is called as ionization. Okay. So molecules in liquid phase needs to be converted into gas phase or gas phase ions for the mass spectrometer to be able to measure them. Mass spectrometer measures mass to charge ratio, often represented or called as M by Z, where M denotes mass and Z denotes charge of the molecule. M by Z ratio of the ions formed by the process of ionization. Okay. So LCMS, that is liquid chromatography hyphenated or combined with mass spectrometer, is a powerful analytical technique as it combines or offers the separation power of liquid chromatography and detection power of mass spectrometer. Now, what are different applications of LCMS? It can be used for identification and confirmation of compounds, that is for qualitative analysis. It can be used for characterization of unknown compounds. That means you can find out a basic or preliminary structure of the unknown compounds which are present in the sample. And you can do a quantitative analysis. That means you can accurately quantify the amount of compound present in the given sample at the trace level. Now there are certain advantages of mass spectrometer over other detectors. So the first is sensitivity. It offers a very high sensitivity as compared to other detectors. Next is selectivity. Now, as the mass spectrometer is dependent on the masses of the compounds, it offers very high selectivity or specificity over other techniques. high accuracy, and robustness. Now, these are some basic terminologies which you would often come across when you will be working on the mass spectrometers. So the first is M plus H ion. Okay. So it is basically the positively charged form of a molecule that is formed when one proton, that is one hydrogen, is added. The ion detected is 1 unit higher than the monosterobic mass of the uncharged molecule. Okay. Now let's say, for example, if a particular compound has a mass of 100, so the M plus H ion of that particular compound on the mass spec would be 100 plus 1. That 1 counts for the proton or the hydrogen which we are adding. So the M by Z value would be 101. The next is M minus H ion. So again, it is a negatively charged form of a molecule that is formed when one proton is removed. The ion detected is 1 unit lower than the monostopic mass of the uncharged molecule. So for a symmetrical molecule whose mass is 100, so the M minus H ion would be 100 minus 1 because we are removing one proton. So the mass would be 99 M by Z. Okay. Then what is mass to charge ratio? Uh, for the singly charged monostopic ion, M plus H of a reserpine, wherein the neutral mass for the reserpine is 608.2 and Z basically denotes the charge. So the total charge is 1. Therefore, the peak will appear on the spectrum at 608.2, which is the neutral mass of the compound, plus 1 for the hydrogen because we are adding one proton, divided by total number of charges. Z, that is charge is 1. Okay, so it is 609.22. Okay, so the on mass spectrum for this particular compound, you would get a peak on the MS spectrum at 609.22. Okay, similarly, let's say this particular compound, suppose it has two charge. Okay, there are two different sites wherein the protonation has been done, so the Z will become 2. Okay, so what you have to do, 608 plus 2, since we are adding two protons, plus total number of charges Z is 2, so 608 plus 2 divided by 2, so it will become 305. Okay, so that's how you calculate mass to charge ratio. Then these are very important terminologies again when you especially work on the mass spectrometers. So the first is monostopic mass. The monostopic mass of a molecule is the sum of masses of atoms in a molecule, considering the most abundant isotope of each element. Okay, so for example, we all know carbon has two isotopes, carbon 12 and carbon 13, right? So out of which carbon 12 is highly abundant. It is highly abundant in nature. So while calculating monostopic mass, you have to consider carbon 12 and not carbon 13. Similarly, hydrogen has two isotopes, hydrogen 1 and hydrogen 2, out of which hydrogen 1 is highly abundant, correct? So for calculating monoatomic mass, you have to consider hydrogen 1. Okay. What is nominal mass? So it is just the monoatomic mass rounded up to the nearest integer. So let's say, for example, the monoatomic mass of a particular compound is 100.12. So you have to round it off to the 100. If a monoatomic mass of a compound is 100.78, so you have to round it off to the 101. Okay. Next is average atomic mass. So average atomic mass of an element is the sum of the masses of its isotopes, each multiplied by its relative abundance of its naturally occurring isotopes. Okay. Now I'll just go on to the next slide to show you the calculations. So as you can see, as we all know, chlorine has two isotopes, correct? Chlorine 35 and chlorine 37, out of which chlorine 35 is highly abundant as compared to chlorine 37. So chlorine 35 is almost 75 or 76% abundant in the nature, whereas chlorine 37 is around 24% abundant. So you have to multiply 35 into its naturally occurring abundance, that is into 75, plus
36.9 into 24.2 divided by 100, since it is given in percentages. So the value which you would get for the average atomic mass would be 35.4 for the chlorine. Okay. So in case of chlorine, the average atomic mass would be 35.4, whereas the monostopic mass, as I have told you, you have to consider the most abundant isotope of that element. So 34.9, as it is highly abundant, you have to consider it for the monostopic mass. Okay. So one thing you have to remember, that while calculating the masses, especially when you work on the mass spectrometer, you have to consider the monostopic masses. Now for this particular compound, with the chemical formula C9H11Cl N2O2, if you look at the average atomic mass and the atomic mass M plus H values for this particular compound, there is a substantial difference between both the values. Okay, the monostopic mass is 215.06 and the average atomic mass is 215.66. So there is a difference of almost zero point 0.6 or 0.7 Dalton between both the values. Okay, so you have to remember this, that you have to consider monostopic masses. Now this is just a small revision of what I have discussed till now. So this is one of the compound which chemical formula is C8H10N4O2. So I have given some of the elements which are present in this particular compound along with their atomic masses, the monostopic masses and average atomic masses. So what you have to do is you have to calculate the monostopic mass, nominal mass and the average mass. So I'll just give a minute to do the calculations and then I'll display the answers. Value you have calculated is correct or not. Okay, so the monostopic mass for this particular compound is 194.08. Nominal mass is of course 194 and average mass would be 194.19. Okay, so this compound is basically caffeine. Okay, so we'll discuss about the different components which are present in the mass spectrometer. Okay, so this is just the basic schematic representation of the mass spectrometer flow diagram. So the first you have a sample introduction system, which is basically nothing but a chromatographic system, which could be either liquid chromatography or gas chromatography. Then an ion source, which basically helps in formation of ions or the source of ionization. Then mass analyzer, often called as quadrupoles or mass filters, followed by detector, and then the software system which basically computes the data and gives you the graphs. Okay. So as you can see, as I have mentioned, the mass analyzer and the detector and the other parts have been kept under high vacuum. Now why vacuum is required in LCMS? Okay, now as I have told you, uh, mass spectrometer generates ions and those ions will have either positive charge and negative charge, correct? So as those ions have charges, they are highly reactive. Okay, so if there are any air molecules which are present in this region, since these ions are highly charged, they will try to interact or collide with those air or molecules or other species. So to avoid that or to neglect or to eliminate that, this particular region has been kept under high vacuum. Okay, so that the ions can safely travel from the analyzer to the detector. Okay, so this is the basic schematics of the MS region. Okay, basically the instrument which you have in which the Bombay Veterinary College have in the lab is tandem quadrupole system. So tandem Then there is one collision cell wherein collision induced dissociation happens, and the ions get further fragmented to form daughter ions or daughter ions or the fragment ions, and those fragments then further get detected in second quadrupole labeled as Q2. Okay, and then they further travel to the detector. So mass spectrometer generate ions of a molecule from the sample with the help of an ionization source. Ions are separated according to their specific mass to charge ratio in the mass analyzer. Ions emerging from the analyzer are detected, and their abundance is measured with the help of the detector that convert the ions into the electrical signals. These signals are then processed by the software, and the results are displayed in the form of a plot of ion abundance, that is relative abundance versus mass to charge ratio. Okay, so in the MS graph on the x-axis you have m by z values, that is mass to charge ratio, and on the y-axis you have the ion abundance of those specific m by z specific masses. Okay. So, as I've told you, ionization is very, very important in mass spectrometer. So there are two ionization techniques which are very widely used in mass spectrometric analysis. So first is electrospray ionization, and the other one is APCA, that is atmospheric pressure chemical ionization. So these two ionization techniques can be selected based on the properties of the compounds or analytes which you are trying to analyze on the mass spec. So we'll just discuss briefly about these two ionization techniques. So the first is electrospray ionization. So as the name suggests, it basically works on the phenomenon of spraying of electrons at the tip of the capillary, okay, to form the process, to initiate the process of ionization and to form the ions from the sample or the eluent which is coming from the liquid chromatography. So the ionization basically takes place at the atmospheric region, and it has three different stages. So the first is formation of charged droplets. So as you can see here in this diagram, a high voltage power supply or the high capillary voltage is applied at the tip of the electrospray capillary to form the ions. Okay, those ions, then the next step is solvent evaporation and droplet fission. Then now the next step is evaporation of the solvent, since the LC eluent has the analytes as well as the mobile phase. So we are so there is a requirement of evaporation of the solvent, since we are interested in ions of the analyte and not in the ions of the mobile phase or the solvents. Okay, so the next step would is solvent evaporation and droplet fission, and the third step is formation of gas phase ions. Okay, these gas phase ions then further pass to the mass analyzer, and then they further move to the detector. Generally, electrospray generates M plus H or M minus ions. Okay, based on the polarity which you have selected. So basically there are two types of modes: positive ionization mode and negative ionization mode. So in positive ionization mode, uh, you would basically generate M plus H ions, and in negative ionization mode you would generate M minus H ions. Okay, so this is the schematic of electrospray ionization. So first you have electrospray ionization probe. The sample is introduced from the chromatographic system. This blue region is nothing but the electrospray capillary. So capillary voltage is applied at the tip of the capillary, which is basically a high voltage power supply to promote or to initiate the ionization. The ions which are formed then further move to the sample cone. Okay, uh, a high voltage is again applied at the sample cone to attract the ions towards the sample cone. So the ions will take a 90-degree turn towards the sample cone because of the high voltage supply. Then they will further move here, and again a high voltage is applied to here in this region. So again ions will take again a diagonal 90-degree turn, and then they will move to the hexapole. Hexapole is basically an ion guide So it basically streamlines the ions, all the ions which are coming from the sample cone, and it further passes those ions to the quadrupole for the further separation. So as I've told you, it can be operated in two modes, positive mode and negative mode. So in positive electrospray ions, let's look at this example. Now, since this has nitrogen in this in the structure, so it can be analyzed in positive ionization mode. So the ionization has been happened on this particular nitrogen here, and you would get M plus H value for this compound is 235.3. Whereas this particular compound can be analyzed in negative electrospray ionization, as it has carboxylic acids as one of the functional group. So as you can see, the mass of this particular compound is 206, and since it has been identified in negative mode, the mass is M minus H, that is 205.2. So the one hydrogen from this carboxylic acid functional group have been removed or abstracted. Okay. So generally, in electrospray, uh, compounds having acidic functional groups would be ionized in negative spray, or rather negative ionization mode, and the compounds with basic functionality or basic functional groups would be ionizing more predominantly in positive ionization mode. Okay. Next is APCA, that is atmospheric pressure chemical ionization. Again, this is one of the ionization technique. So in APCA, the liquid flow coming from the LC element is forced through a narrow capillary to give it a very high linear velocity. The APCA probe heater, as you can see here, it is combined with the nebulizer gas, which vaporizes the liquid flow. So nebulizer gas is nothing but the nitrogen gas flow, which helps in nebulizing, that is to form a fine mist or the spray of the solvent which is coming from the liquid chromatography. Okay. Now this APCA probe or atmospheric pressure chemical ionization probe is heated at a very high temperature ranging from, let's say, 400 to 650 degrees Celsius to evaporate the solvent which is coming off from the LC element. Okay. Now the solvent and the analyte vapors then passes or moves through the corona discharge pin. Okay, so this is the corona discharge pin, as you can see here, and a high voltage has been applied at the tip of this corona discharge pin or corona needle, which basically helps in ionization of the uh, liquid of the vapors or gaseous phase vapors which are coming from the APCI probe. Okay, so that is the main difference between the electrospray ionization and atmospheric pressure chemical ionization. Now if you have looked carefully in the APCI probe schematic diagram, the tip of the capillary is slightly inside the probe. Okay, because it functions on the heating the APCI probe at a certain high temperature, and then the vapors further move to the corona discharge pin. Whereas uh, if you look at the electrospray capillary, it is outside of the probe. Okay, and we apply a capillary voltage at the tip of the electrospray capillary. Okay, whereas in case of APCI, this capillary is inside the probe because of the difference in the ionization techniques of these both the ionization sources. Okay. Okay, so the solvents and analyte vapor will further move to the corona discharge pin, which has been applied with a very high voltage. The molecules will get ionized and then further move to the sample cone. So what is the basic difference between electrospray and atmospheric pressure chemical ionization? In electrospray, as I've sorry. So in electrospray, as I've told you, the ionization happens in solution, whereas in APCI, it happens in gaseous. It is basically a gaseous phase ionization. Both the techniques can be used with reverse phase or normal phase chromatographic techniques. In case of electrospray ionization, the probe is not heated. Okay, we apply a capillary voltage to promote the ionization, whereas in case of APCI, the probe is heated at a certain high temperature ranging from 400 to 600 or 650 degrees to promote the vaporization, and then further it moves to the corona pin. In case of electrospray, we have or we apply a capillary voltage, okay, whereas in case of APCI, we apply a corona pin or corona discharge pin voltage. Okay, so that is the basic difference between electrospray and APCI. In electrospray ionization, it will show a very strong mobile phase effect. So what types of buffers or additives which you are using in the electrospray ionization will have a strong impact on the response of the analytes in electrospray. Whereas in case of APCI, the mobile phase effect will be comparatively low. With electrospray ionization, you can analyze compounds which have polarity from mid polarity to high polarity, whereas less polar compounds can be analyzed with the APCI. Electrospray can be used for thermally labile compounds, whereas APCI could be slightly unstable for thermally labile compounds, as the ionization involves high temperature at the APCI probe. So compounds which are thermally labile, there are chances that those compounds may get thermally degrade or thermally decompose because of that high temperature. Okay. Again, as electrospray applies a very high capillary voltage, you can use it generally between the LC flow rate of 0.1 to 1 ml per minute, and generally you should split a flow more than 0.8 ml per minute, whereas APCI can be used at very high flow rates as compared to ESI. So this is just the basic comparison of what type of molecules can be analyzed using ESI and APCI. So as you can see, APCI can be used for non-polar to mid-polar compounds, whereas ESI can be used for mid-polar to highly polar compounds. APCI can be used for compounds with lower molecular weights to mid-range molecular weights, whereas ESI can be used for lower as well as higher molecular weight compounds. So generally, electrospray ionization can be used for analysis of higher molecular weight compounds such as proteins and peptides. Okay, now we'll discuss briefly about the mass analyzer, which is basically helps in separation or sorting of the ions which are coming from the ionization source. Okay, so the quadrupole or the mass filter basically consists of 4 parallel molybdenum rods. These rods are equidistant from the central axis. Now, as you can see here, the opposing rods have same polarity. Okay, so these are the opposing rods and they have same polarity, and the adjacent rods have opposite polarity. Okay, so these are the adjacent rods and these two rods have opposite polarities. A combination of DC and RF voltages, that is direct current and RF voltages, which is supplied to the instrument, are applied to these rods. The combination of these voltages basically separate the ions based on their mass to charge ratios. Okay, so basically let's say suppose there are 3 different ions with 3 different MBASI values. Let's say ion A has MBASI value of 50, B has MBASI value of 100, and C has 150. So the lighter ion, which has a lower MBASI value, will travel or moves first from the quadrupole, followed by the heavier ion. Okay, so ion A being the lightest having a smallest MBASI value 50, so it will travel first as compared to B. Then B being having MBASI value of 100, it will travel after compound A, and C being the largest, having the largest M/Z value 150, it will travel after after the ions A and B. Okay, so this is how basically the sorting or separation of the ions takes place in the quadrupoles. So at a given set of voltages, only a single M/Z value will have a stable trajectory along the length of the rods and allowing the transmission to the detector. Now suppose in the software, if I give a command that only blue ions should have a stable trajectory and all the other ions should be get rejected, so only blue ions or the will have a stable trajectory through the quadrupoles and then they will move to the detector. All the other ions will be get rejected or deflected in the quadrupole. Okay, so that's how you increase or improve the selectivity or specificity when you work on the mass spectrometers. So there are different modes of operations by which mass spectrometer can be used. So the first is selected ion recording. Second one is multiple reaction monitoring. Third one is parent ion scan, and fourth one is product ion scan. Okay, so the first two options, that is selected ion recording and multiple reaction monitoring, these two modes of operation can be used for quantitative analysis, that is to determine the amount or concentration of particular analyte present in the given sample, whereas the other two modes of operation such as parent ion scan and product ion scan can be used for qualitative analysis, that is to identify the structure of the unknown compound which is present, structure or rather mass of the unknown compound which is present in the sample. Okay, so selected ion recording means only a parent mass or the precursor ion will be identified and used for the quantification. So as I've told you, there are two quadrupoles and in between two quadrupoles we have collision cell. So let's say a particular compound has mass of 381.2. So in selected ion recording or single ion monitoring, both the quadrupoles will be kept fixed and the particular M/Z value will then move or the ion will move from the first quadrupole through the collision cell and to the second quadrupole. Okay, so in selected ion recording, you can only use a parent ion or the precursor ion or precursor mass for the quantification. Next is multiple reaction monitoring. So as the name suggests, you can make use of multiple masses for the analysis of a particular compound. Okay, so let's say for the same compound having a precursor mass or the parent ion mass as 381.2. Okay, so in this case q1 will be kept fixed. This particular ion will then move to the collision cell, wherein collision induced dissociation will happen with the help of an argon gas, wherein the fragment ions or daughter ions will be formed, and those daughter ions, so out of these daughter ions you can select a particular daughter ion for the further monitoring. Okay, so that's why it is called as multiple reaction monitoring. Next is scanning mode, which can be basically used for qualitative analysis. So in parent ion scan, suppose if you want to find out mass of a particular compound or the parent mass of the particular compound, so in that case Q1 or the first quadrupole is kept for in scanning mode and the second quadrupole is kept in fixed mode. Okay, so the first quadrupole will scan all the masses within the given range. Okay, and then a particular mass which you are trying to identify, it will move to the from the second quadrupole. Next is product ion scan. So here in this case we are basically trying to find out the different fragments or daughters of a particular parent ion or a precursor ion. So that's why the second quadrupole is kept in scanning mode and the first quadrupole is kept in fixed mode. Okay, so let's say suppose if you want to identify daughters of this particular fragment ion, so this particular ion will move to the collision cell, wherein the fragmentation will happen by applying a particular collision energy and an argon gas, Then those daughters will then further move to the second quadrupole, which is in scanning mode, and those daughters can be detected. So based on the mass fragmentation or by identifying the fragment ions or daughter ions, you can find out or determine the structure of a unknown compound. Okay, so this is just an animation just to make you understand how it works. So this is the mass scan mode, which can be used for qualitative analysis, that is for identification of molecules or compounds. Now let's say if I give a range of, let's say, 50 M by Z to 500 M by Z. So all the ions which are formed and which falls within that range, all the ions will be get scanned in the quadrupole, and each of the ions will move to the detector, and you will get spectrum for all those compounds. Okay, so this is called as scanning mode. So the next is fixed mode, that is selected and recording. Now let's say there are two conditions. Condition 1, ions of specific M by Z value, that is only red should be detected if you give this command in through the software. So as you can see, there are two ions, blue and red, but as you have given command from the software that only red ions should be detected, so the blue ions are getting deflected in the quadrupole, and only red ions are reaching to the detector, giving you a spectrum. Similarly, in the second condition, suppose if you mention that only blue ions should be detected, then red ions are getting deflected or rejected in the quadrupole itself, and only blue ions are moving to the detector. Okay. So this is how mass spectrometer offers specificity or selectivity over other techniques. Okay. Then further we'll move on to the detectors. So there are two types of detectors which are employed in the mass spec. So first is electron multiplier and the other one is photomultiplier. So out of these two, photomultiplier tube is the most widely used detector in the mass spectrometers. So basically these detectors multiplies the incoming signal from the quadrupoles in order to produce a strong enough signal or electrical signal that the software data system can be used to convert it into a readable format. Okay. So this is how generally the mass spectrum looks. So on the x-axis, you have mass to charge ratio or M by Z values, and on the y-axis, you have relative abundance of those ions uh, which are formed. Okay. Now this is very critical when you work, especially on liquid chromatography hyphenated with mass spectrometers. So there are certain precautions which you need to take care. So as I have told you, mass spectrometer works on the process of ionization. So the mobile phase solvents, buffers or additives which you use as a mobile phase in the liquid chromatography, they should be volatile. Okay. Suppose if you use as I've told you, the mass spectrometers works on very high voltages and high temperatures. Suppose if you use non-volatile salts and buffers, those non-volatile salts and buffers will not get vaporized or ionized, and they will form a salt, and they will hamper the performance of the system. So I have made a list of some of the MS compatible additives and buffers which can be employed for LCMS applications. So you can use additives like formic acids, acetic acid, trifluoroacetic acids. So these additives can be used as an additives for the LCMS applications. Some of the buffers such as ammonium acetate, ammonium formate, ammonium hydroxide or ammonium carbonate can be used at lower concentrations as buffer for the separation on liquid chromatography when you work on LCMS. Uh, these buffers which I have highlighted in red color, such as phosphate, citrate buffers, borate, ion pairing reagents, surfactants. So these buffers and surfactants or reagents are not recommended to use when you work on LCMS applications. Okay, since these are non-volatile buffers. So this is just a picture of the sampling cone when one of the user has used non-compatible mobile phase solvents and buffers on the mass spec. So as you can see, there is a clear deposition of the salt because of the use of non-volatile buffers into the mass spectrometer. So just to avoid such kind of scenarios, it is recommended to use MS compatible buffers and solvents when you work on the LCMS applications. So that is all from my side. If you have any questions, please go ahead.
Dr. Anup Kumar Krishnan is also joined with us now. So I welcome you, sir.
Good afternoon.
Yeah, very good.
Right?
Yeah. So yes, so in this today's afternoon session, we have Dr. Anup A. Krishnan sir with us, and he is going to deliver a talk on sampling, traceability, sample storage, and sample preparation procedures in our today's training session. So before to begin with our today's talk of Dr. Anup Kumar sir, I would like to just give a small introduction about Dr. Anup Kumar Krishnan sir. So Dr. Anup Kumar Krishnan sir is working at Export Inspection Agency, which is a laboratory under Export Inspection Council, Ministry of Commerce and Industry, since July 2007 on various capacities. Presently, Dr. Anup Kumar Krishnan oversees the activities of the EIA and Kochi laboratory. He is having 20 years of experience in residues and contaminant analysis. Dr. Krishnan has completed his Doctor of Philosophy on Biosciences from Bangalore University, Karnataka in the year 2009. Afterward, he has worked as an international consultant on deputation for the FAO and IAEA to Educator, Ghana and Bangladesh. Dr. Krishnan also has 7 years of research experience with 9 international publications on peer-reviewed scientific journal, 1 chapter in an international book and few papers in national scientific journals. Dr. Krishnan is a recipient of the Young Scientist Award of the AOAC India section 2018. Dr. Anup Kumar Krishnan sir has undergone various trainings on the master trainers at University of the Maryland, USA for a trainers program on veterinary drug residues in meat, poultry and fish. Mycotoxins at Technical University of Munich, Germany. He also underwent end-to-end training on latest microbiological techniques at Danish Technical University, Denmark, and training on sampling of the food products at Valencia, Spain. He is a member of Indian delegations of the Codex Committee on Method of Sampling and Analysis. Dr. Krishnan is also a member of the Rapid Analysis Food Testing Committee of FSSAI and special invitee to scientific panel on methods of sampling and analysis. Dr. Anup Krishnan is also trained and qualified assessor of NABL as per ISO 17025 and ISO 17034. He is also a trainer at ITC FASN Mumbai. Dr. Krishnan has recent focus area is on developing analytical tool on food authenticity and food fraud. So such a huge experience today we have in our today's session. Dr. Anup Kumar Krishnan is with us, and I would like to request to Dr. Anup Kumar Krishnan sir to please begin with his talk and start with his lecture. Anup Kumar sir, please.
Thank you. Thank you, sir. Thank you so much for the introduction, and I would also like to thank ICR, NH, EP, and CAST, along with the Mumbai Veterinary College, for inviting me for the program, and in special Dr. Zende, who has been associated with me from long time in various forums and capacities. So I am just sharing the folder. Is it visible now?
Not yet.
Now is it visible?
No, sir, not yet still.
Is it visible? No.
No, sir.
Now?
We could read the message that you are trying to share the content, but still it is yet to visible.
I think it may be coming. Still it is not visible to anyone?
आ रहा है क्या देख? No, sir, still it is not visible.
Let's check it.
Sir, do one thing. You please share the entire screen so that I think the PPT can be visible later.
Okay.
You share the entire screen, sir.
Now? Now I shared the entire screen. Is it visible now?
No, not yet.
I think someone has written it is visible. I think someone has sent a message that it is visible.
Madam, it is not visible. I think you
It is
can
not-
just no, not it. You just open your PPT and then you share.
No, the PPT is open. Already the PPT is open.
Okay, you unshare and then share PPT. Dr. Meshram, you can check from your side also.
Yes, sir. Yes, sir.
Are you permitted him to share?
Yeah, we are checking, but it is not visible on the screen.
अनुप आप एक बार अनशेयर करो उसके बाद शेयर करो.
अभी आ रहा है?
नहीं, अभी भी नहीं आया.
एक मिनट. I am sharing the entire screen.
सर एक बार आप लेफ्ट करके वापस ज्वाइन करके वापस शेयर करके कोशिश कीजिए.
एक मिनट.
Some technical issue.
You can log out and then you join and share. Yeah. डॉक्टर मेश्राम अश्विनीला पण चेक करायला सांगा जरा इकडे.
Yes, sir. Yes, sir. We are checking, sir. कहाँ से किया? Yeah, Anukumar sir. Now it is visible. I think he is yet to join. Join, no?
Is it visible now? Is it visible?
Yeah. It's very much visible now.
Yeah. Sorry,
Yeah.
sorry for that. I think it is a technical glitch.
Yeah, no problem, sir.
So once again, good afternoon to all. So I'd be just briefing about a small overview with respect to, I think it's a hands-on training on the antimicrobial residue analysis in chicken meat on using liquid chromatography with mass spectrometry. So I'll be just speaking a brief about sampling, the traceability part, sample storage, and how sample preparation techniques are presently there, or what are the advances which has happened, and also talk a bit onto the challenges associated with that. So I would also touch on few of the antimicrobial substances which are of interest, and just a brief on these topics which we have discussed. Just to touch on, I think it is known to, I think, almost all participants. I think past 2 years we have been having this program. So mainly these antimicrobials, including antibiotics and antiviral or antifungal, are mainly being used to prevent and treat infections in humans, animals, and plants. It is being used also in poultry farms, mainly to improve meat production. Farmers also use it. So the problem here is mainly on the abuse of it, or antimicrobials are being used, and the residues are mainly remaining. That is where our concern is there, and that is where our analytical tools are being used to identify whether these antibiotic or antimicrobial substances are in the residue form. It is available in this animal origin products. See, there is a worldwide categorization which is happening in antimicrobials. Mainly, it's based on the risk. So they have categorized it into category A, category B, C, and D. So there are some compounds which are, this I'm telling it is mainly a categorization in European Union. In India, FSSAI already has categorized it into banned compounds and compounds which is having tolerance, or where MRLs or limits are being prescribed. So when this is there, see, they categorize it into group A, group B, group C category, and group D, wherein which mainly group C and group D are the antimicrobials which are generally being used. And in the absence of group C and group D, group B is permitted to be used, and group A ideally is not authorized for use in any of the animal origin products. I'll come to the basic categorization or new the class approach which is being followed by European Union. So what they do is they classify it into clearly group A and group B substance. From that group A, B, C, which we found, which we have already seen in the previous slide, they categorize it into two groups. Group A is completely prohibited or unauthorized pharmacologically active substance. Group B are pharmacologically active substances which are used or permitted. That means group B has limits or MRLs, wherein which some toxicological study has been done, based on which the limits has been prescribed in all animal origin products, whether it is meat, whether it is fish, milk, honey, or by that matter any other animal origin product. So you can see most of these compounds are covered. Many of the antimicrobials are being covered. There are some steroids, stilbins, which are being covered. There are crocodiles. There are antiviral substances also. When it comes to group B, again you can see some antimicrobial substances, and other pharmacologically active substances are also covered in this classification. Now, when it comes very specific to antimicrobial drugs, you can see these groups. These are mainly the groups which are covered in the antimicrobials, that is aminoglycosides, amphinicols, beta-lactam, fluoroquinolones, macrolides, nitrofurands, sulfonamides, and tetracyclines. See, when you go to these groups, within these groups, you can also understand that there are some compounds which are banned, like nitrofurands. Nitrofurands are banned in nature, and it is not permitted in food of animal origin. While there are other groups like sulfonamides, tetracyclines, fluoroquinolones, there are these groups where MRLs are there, and these are permitted, and still we monitor them because it should not go above these MRLs. Now, when it comes to the analytical sample flow or the workflow diagram, this is how it happens. So the cycle starts from, I think, sampling. So then the sample is being transported to a lab. Then we do the sample preparation. Then we do the analysis. Then we have a process of data handling. And after the data is being processed, we come out with a decision. It can be informed to a customer, or if it is a research institute, it goes into your, as a part of your research purpose, publications, or it can also come as an advisory or an information to the various regulatory bodies or governmental organization, on the basis of which some decision is being taken. This is how generally a flow happens with respect to any, whether it is an antimicrobial or an antibiotic residue workflow. Now, coming to the first topic of it, sampling. See, that it's very simple, but many thought process in, even if you see in a research organization, by that matter, if it comes to a regulatory body, the thought process maybe before 2010 and all was that everything we can do anything, we can find anything or everything through an analytical tool. But that is not the case. If you are not drawn a proper sample and submitted it for testing, there is no meaning in finding out that we could get an antibiotic or we couldn't get an antibiotic, because improper sampling can invalidate a test result. So the sample which we draw should be actually true representative. If it is not a true representative of the whole group or a group of animals or a group of particular product or a commodity, it will not be a true representative, and the results will not have any meaning of it by that matter. So what is the importance of how we do a sampling? Sampling is actually selection of a certain portion or number of containers or products. I'm talking about food products, how it is happening. Ideally, it should be a proper selection. For that, we should have a statistical tool. Now, in case of exports, from where the background in which I come from, an organization, we have specific sampling protocol for each product, whether it is milk, whether fish, meat, poultry, or whether it is even plant origin product. We have specific sampling protocols or sample selection criteria. And based on this, we draw around, generally the representative samples being drawn from a lot or a consignment is 1 kg. And that 1 kg comes to the sample, comes to the lab, sorry, not to the sample, comes to the lab for testing. So that is how representative sample is drawn. And there are different types of sampling. Random sampling. Random means there is no uniformity being maintained. Some samples are being drawn for specific research purpose. Some sampling protocol is there for monitoring purpose. Like we have monitoring a pesticide residue at national level, which is being done by Ministry of Agriculture. Same way, monitoring is being done by Export Inspection Council also for all animal origin products, milk, honey, meat, shrimp, aquaculture products, all are being done. And the last type of sampling protocol being used is targeted sampling or risk-based sampling. We have a risk-based that is being adopted presently by FSSAI, which commodity has a risk, they do a specific type of sampling. Now, this is how sampling happens. Just to give you a representation, we have a big lot from which a small sample is being taken, and that sample is further being treated or reduced using any subsampling protocol. Some people use coning watering if required. Generally, it is being used in animal origin products. However, if it is a big animal origin, plant origin product, however, if it is a big animal origin consignment also, where in which the quantity of the sample taken is more, we can do subsampling, because the analytical portion required is 5 grams to 10 grams. So based on that, we can take a decision whether after sampling, a subsampling is required or not. Now, after sampling, the sample comes, I think in the initial flow I have shown, after sampling, it goes to the laboratory. So that is where the actual transportation happens, and the sample is being handled in a laboratory. So the most important thing is to ensure chain of custody. That is, that chain of custody means that the sample is being transported in proper environmental condition. Now, environmental condition means animal origin products ideally should be transported in a proper temperature condition. So ideally, we tell that it should be maintained at -18. However, we need to check the temperature conditions during the transport. Now, second is integrity of the sample should be maintained during the process, that it should be properly sealed and intact, it should be there. Again, I told when the sample is being received in a laboratory, ideally the temperature condition should not go beyond 4 degrees. I'm talking about chemical testing. In case of microbiology, the requirement will be more stringent. It can go even up to minus temperatures, in which, because we are touching on various microbiological, including pathogens. So the criteria may be slightly different. So once it is received in the lab, the samples are coded with a unique code, and that code will be there. This is to ensure confidentiality in the process. Because see, if a sample comes to a customer in a lab where it is testing, you know already the customer who has submitted the sample, there is every possibility that there would be a probability of confidentiality breach. So a code is being put, and based on the code, that would be the life of the sample, and it goes inside the laboratory for testing, or traceability of the sample is being maintained through this unique code. Now, if testing is being done after some time, like you have multiple analysis to be done or multiple parameters to be done, even in the case of antimicrobial, you will have different methods. In such case, the sample has to be stored at -18 so that the integrity of the sample is being maintained. So sample accountability becomes always an integral part of any audits which happens in any laboratory, by that matter, whether it is a regulatory audit or it is being done by a customer or by an accreditation body. So after this, we take it into the laboratory. The actual lab process starts. So the first of the processes that you need to convert the lab sample into a test sample. So because we have 1 kg of the sample, however, we require only for testing 10 grams, mainly for antibiotic residues, or even 1 to 2 grams also. So what we have to do, we need to process the sample, remove parts which are not required. Mainly, ideally, they tell the edible part has to be taken for testing. Because that is what we, as a human being, as a part of food safety, we consume. So what we will do is we will do the homogenization or mixing or whatever process it is there to convert the lab sample into a test sample, or reduction happens. So ideally, the whole 1 kg is homogenized, and from that homogenized 1 kg of the sample, we take the representative sample for testing. So now during this process, people tell that, yeah, I put it into a mixie, I homogenize it. That is enough for us to take the to consider it for analysis. But that is not the case ideally, because if you are not done proper homogenization under proper environmental condition, the residue which is remaining, actually which is available, or the target residue in the sample can deteriorate, or it can also degrade due to different conditions within the processing. So that has to be ensured as a part of the initial part of the analysis or sample processing. Now, once samples are processed through in some cases, like if you go to many of the laboratories where they feel that once you homogenize the sample, there is a process that heat generation can be there. To avoid heat generation, where in which some residues can degrade. So that is why they use dry ice for homogenization as a part of it. So that it's like cryogenic grinding, cryogenic homogenization. So that is a good practice which is being followed even in meat products. Many people do dry ice, use dry ice as a part of homogenization. After homogenizing, the test portion comes to us, and the test portion is the first, the actual analytical portion which is being taken for further testing. So this is how always a thought process comes with many people. Why is sample preparation required? Ideally, why is it required? See, now the problem is any sample by that matter is organic in nature, and it cannot be directly analyzed in a liquid chromatography or NC-MS or mass along with the tandem mass spectrometry. So what we do is there are 3 procedures which ideally can be there. Or 3 scenarios which can be there. The sample can be too dilute. So if samples gets too diluted, what will happen? We can't quantify it. We may not be able to quantify it because the sample may have residue, but you may not be able to quantify it. The sample can be too dirty in the sense organic. Lot of organic matrices will be there. Lot of interferences can be there, due to which we can't target the actual analyte. See, there are also problems that it can contaminate your instrument, your column, your instrument, and your cone associated with the mass spectrometry. So for all these things to be avoided, what we have to do, we need to prepare the sample. So we should use an optimal ideal sample preparation technique. And again, to give you also the importance of sample processing, many people don't understand that. We all think that we have an LCMSMS, and if we put anything into the LCMSMS, we'll get a result. So sample processing is equally important, because if you do a mistake there, the whole result will be wrong. So you can see what are the sources of error. 30% of the error contribution comes from sample processing. That is how the error percentage. See, sample introductions, these are all very, very negligible, not much, within 10%. But however, the sample processing contributes to 30%. Now, in time spending, if you go to the next side of the graph also, you can see around 61% or more than 60% of the time also we spend in sample preparation. So you can understand how important this particular area is. Identifying a proper sample extraction or a processing method. Now the whole flow is there, and always just again to substantiate that sample preparation is often the bottleneck, and that makes the whole process very slow, intensive. Many people lose their analyte during sample preparation, because instrument can only detect. If whatever you put it into the instrument, it will detect. But if you don't prepare the sample properly or extract the sample out, actual analyte, you will not be able to achieve the final target. Now, there are something which happens in the whole process, which also people should understand, people who are working in the lab, that is called contamination. What are the sources of contamination? Sources of contamination can come in sample collection, during sample transportation and storage, during sample preparation. That means your homogenization, which we discussed, through glasswares, through other source, mainly through glasswares it can happen. In sample analysis, it can come through carryover, through memory effects. Memory effects means one sample has gone through the column, it can contaminate the column, and the next sample, which may be a good sample or it may not have a residue, can take that contamination in the column and come out and gives a wrong indication that the sample is having antimicrobials or antibiotics by that matter. So these are some in a laboratory, people should be very vigilant that these are the sources of contamination which can come through different chains. Now, when it comes to the action analytical step of extraction, there are different types of extraction. We will now come to the sample processing. What are the different types of sample processing available? So the extraction happens. So there can be a solid liquid extraction. Old extraction techniques were like that. Liquid extraction is there. Now the new techniques have come, something called quenchers or dispersive SPE methods, where in which separations or filtrations are happening, and then dilution and a cleanup. Cleanup generally is through immunoaffinity columns or solid phase extraction or through quenchers method. So, but I'll come to the details of it now in the subsequent slides. So I told if we have a easy procedure, what would we do? We will put 1 gram or 5 grams of the sample. You put a solvent, dilute it, take the extract and shoot it. That would be the ideal situation in analytical field. But it is not the scenario nowadays, because once you are treating animal origin products where fat content is there, lipids are there, and many other associated interferences are there, we have to have a proper extraction and a cleanup procedure. So dilute and shoot, liquid extraction, solid liquid extraction, and solid phase extraction. These are the different types of extraction presently available globally and presently being adopted for antibiotic residue analysis. Now, let us understand what is extraction. What is the basic principle of extraction? The basic principle of extraction is to withdraw the analyte actually into a liquid medium. Using some solvent, because now it is in an organic, like meat. I'm telling, meat is in an organic form. You need to extract that particular analyte or an antibiotic or an antimicrobial compound from that particular tissue, which is bounded with the tissue, remove it onto a solvent medium, and from there what we do is we do different types of miscibilities or associated extractions, so that there will be a differentiation between the actual analyte and the interferences. So that is why what we do is we do centrifugation or filtration. so that whatever interferences from the analyte is there, that will be removed and only the analyte remain on the final extract. But what is happening is when we do such extraction, the problem what is happening, there may be fat or lipids which are associated. When such things are there, we need to use the other chemicals. Like in case of quenchers, we use magnesium sulfate. Some people use it, and we also use some salting techniques using C18 to remove. C18 is mainly used for to remove lipids and fats. So we use such additional chemicals as a part of cleanup. That is where we want to only have the actual analyte from the solvent and not any other interferences. This is how generally nowadays what extraction procedures are generally being followed for all antibiotic analysis. It is solid liquid extraction or a liquid liquid extraction which happens using different SPE cartridges. Earlier what we used to do, we used to have what is that big extraction vessels where in which you will use a solvent, we will extract it physically, and it was very laborious. Now it is come out with ready-made packets and ready-made solutions are being provided by different suppliers. Now the next after this will be filtration. Filtration is generally done using syringe filters or different types of filters. Why these filters are being used? So that the final extract which we put it into the into the instrument is clean and it doesn't affect the instrument, which I was telling. Because what you put it inside the instrument, your instrument can go bad, like your column, your cones, your pump, everything can go bad because if the particular final extract has some interference or some matrix still which is remaining, and this can affect the LC-MS instrument which is being used. Now you should also understand few things while doing this. You are seeing the different process of extraction now. Like you extract it, you do a process called centrifugation, then you do a cleanup, and then you come out with a final filtration, and then you inject it. Now doing this, all these process, from this process there can be a loss of the actual analyte too. So that should be, we should be vigilant. So there can be some residues which can be volatile. Some chemical reaction can happen, hydrolysis or oxidation, through which there can be a loss, and the actual true analyte can be lost. So you should be very, very careful that some residues or antibiotic residues are very pH specific. Mainly we should maintain a pH of 7. If it goes into an acidic medium, we will not capture, we will not be able to retrieve that particular analyte. If it goes to a basic medium also, we have a problem. So you should be very vigilant how those analytes, we should ideally, if you ask me, we should understand the chemistry of the molecule. If you don't understand the chemistry of the molecule, you will have a problem. We will think that somewhere some other problem is there. Ideally, it is how we tune our sample preparation techniques. Then presence of other metrics, components, temperature can also be part of it, and how much time you expose the analyte. The faster you extract, the better you can come out with the target analyte, because some target analytes can metabolize. Some target analytes can also is prone to temperature and also to light. So you should be careful. Now, what would be the implication? A good sample will become bad and a bad sample will become good. This is where the problem exists. Ideally, that particular sample had some antibiotics, but when you extracted, you couldn't recover it, and we will tell that the sample is free from antibiotic residue. However, it is present. The same way, if we are going through a process and there is some contamination which is coming in the source, we can tell a good sample as bad also. So you should be vigilant. So it's like a permutation combination where you need to work out for developing a good method. Now, ideal antimicrobial targeted compounds presently of animal origin are sulfonamides. We have a very big group of sulfonamides. We have quinolones, including fluoroquinolones generally, and tetracycline groups. These are mainly the groups where MRLs are there. I'm talking about MRLs where compounds are having MRLs. These are generally the compounds which we target. So earlier method, if you ask me around 4 years, 3 to 4 years back or 5 years back, many of the laboratories were using separate method for sulfonamide, separate for quinolones, separate method for tetracycline. So it was laborious. Like each time you have to extract 3 extraction method, 3 LCMS. You need to have 3 extracts and 3 method run in the LCMS also will be 3. So it was really laborious. Same thing was for the banned compounds like nitrofuran, we have one method, and chlorophenicol, we have a separate method. So what happened? The people started thinking about new processes called multi-class. You can see in the previous slide, it is 3 different classes. So people started thinking about new methods called multi-class, multi-residue method. And over the period of time, many new methods were developed using combining all these 3 groups together as one method, like fluoroquinolones, sulfonamides, and tetracycline. I am only telling these groups. There are methods developed in US and Europe where the methods, if they monitor around 100 antibiotic residues in one run, including around 6 groups. So in India, this was a focus point for us. So what we did is we developed a method in fish, which is now also applicable in meat and meat products, which we combined all these 3 methods. We had a good method for extraction with a combined cleanup for all these 3, which was around 1 hour, and the runtime was only 9 minutes. So you can understand the time reduction of these 3 groups to 1 group. So it was a single test. We had 3 groups together, and we targeted around 24 antibiotic residues in one run. And just to give you also flow chart, see this method is published also now, so it is available in public domain. We took only 1 gram. The purpose of taking 1 gram was to reduce the old matrix effect. We used acetonitrile, which was also acidified, centrifuged it, and the acetonitrile layer was dried, and then further NXane was asked to defat it, and the whole thing was filtered and injected. And the whole procedure took only 1 hour, and the extraction and the final analytical method in the LCMS was around 9 hours. And this was published in Food Chemistry, and that was in 2018. And very recently, in 2022, just I think 2 months back, or 1 month, we can tell 1 month back, in December, we published one more method on considering all nitrofuran metabolites in one run, and we validated this method as per the new regulation, which is now in force. So this was around considering all 5 metabolites of nitrofurans in one run, so that it will be useful for analytical fraternity and also trade, because it will it will save a lot of time for us, and also the cost involved in the whole process. Now, the challenges which comes, just wanted to tell. Now, when it comes to animal origin, mainly poultry and meat and meat, we have muscle, kidney, liver associated with that, and all these products all these matrices or sub-matrices goes into the analytical part. So we have this matrix diversity, which will be the first challenge, and matrix composition, which I told you, will have lipids, proteins, carbohydrates, water, salt. We need to remove all these interferences. That is where the extraction challenge starts. Remove all this, remove all covariate. We should have a proper, for which you should have a proper extraction cleanup method and reduce all the matrix effect. And after that only we can inject it. So that is a basic challenge. And this challenge is going to remain as long as until and unless we have a method wherein which we can directly keep a sample and get the antibiotic residue without any extraction procedures. So it's a fine tuning based on the matrices. We need to work. Egg, we will have more challenge, some other challenge, because we will have high fat content associated with that. So you should be a little watchful with the egg, wherein which more lipids also will be associated. Honey will be different. Poultry will be different. So we need to finely tune our methods or extraction methods for the such analysis. So to nullify these challenges, ultimately our purpose here is to have to reduce error, have better sensitivity, have reduced matrix effect, however attain our analytical scope with a fast, reliable and harmonized multi-class, multi-residue method. That would be the ultimate aim of having an analytical method. So which will help for people to work on a faster basis and come out with the better results on a lesser time. Now, challenges, I told you, one more challenge is from single residue to multi-residue, achieving sensitivity. we are all are working onto this, because one method will take a lot of time, and it will take more man days, and it will take also the time being incurred onto it. So the ultimate purpose will be to have more analytes in one run in a single go, which would help lab save a lot of time. So just to summarize also, see this revolution has occurred past 10 years in residue analysis, where mass spectrometry has opened many doors for multi-residue analysis. See, from a single cord to a last generation mass spectrometry has come out. Earlier, people were working on single cord or normal LC, liquid chromatography. We didn't have a mass spectrometry at all. Now we have MSMS, we have high resolution mass spectrometry, where in which we can even go to the accuracy of the, we can also determine the mass accuracy also with many of the compound. Comprehensive residue analysis with the generic sample preparation technique is the need of the hour. Many, including I think many research institutes are working towards it. But ideally, the only problem with when research institutes comes out with a publication is they work on a method. However, they run some samples and see that they are getting good recoveries, and feel that the method is working. Ideally, whoever develops a method, whether it is in a research institute or it is any organization, ideally the method should be validated, and then only you can tell that the method is fit for purpose. So if you do validation, the method becomes more rugged, robust, and reproducible. In any condition, in any laboratory condition, whether it is this lab or whether it is another lab in Europe or in the US. So that is the case. It should be ideally for any generic sample preparation techniques. Thank you. Thank you for the time given to me. And just to give you a precise, I didn't go into very elaborative this thing. I went only onto areas where ideally what is happening presently in antimicrobial residue analysis, and what should be the areas of focus, and what are the challenges being faced. Thank you.
Thank you so much. Thanks a lot, Dr. Anup Kumar Krishnan sir, for your elaborative information on the sampling, traceability, sample storage, sample preparation, and a lot of information regards to all these activities, and even within a recent publications in the very informative knowledge about all your topic which you discussed over here. So here with I would like to ask if any queries, any questions, any point of discussions, and we would like to all the participants would like to ask some questions to the speaker, Dr. Anup Kumar Krishnan sir. So they are most welcome. The participants can also write their questions in the chat box, and we can discuss, and sir will answer for the queries. Any question? Yeah, you just please switch on the mic. Sir, one question from the participant.
Yeah.
Sir, I wanted to ask, like you said that we reduce the sample size to reduce the matrix effect in extraction. Sir, if we reduce the sample size too much, then the dilution factor will go low, and then our final values will be affected or not?
Yeah, that's what I also told in the previous one of the slide, that if you dilute it too much, the actual analyte will not be targeted. So what we did is, when the method was developed, we worked with 1 gram, we worked with 2 gram, and we worked with 5 grams. So what happened is, when we worked with 5 grams and 2 grams, the matrix effect was slightly more. To reduce the matrix effect, we reduced it to 1 gram. However, we were able to achieve all the analyte. Why? Because the group which we selected, sulfonamides, tetracycline, and quinolones, had MRLs. MRLs means these limits were above 100 ppb. So we could easily achieve the required targets with their LOQ. Now, when it comes to low ppb level, like chloramphenicol, where the requirement is 0.3 presently by FSSI, and nitrofuran, when it is 1 ppb, then when you come to 1 ppb, if you take 1 gram, then achieving such the capability at this low level with reduced weight would be a challenge. That is where we need to work a bit on the permutation combination with respect to the weight of the sample, and also with respect to the different extraction techniques.
So, sir, like if we validate a protocol and then we claim that with this protocol, my LOD or LOQ is this much. So, while calculating that, do I have to consider the dilution factor, or if I'm doing matrix match calibration, then I don't need to do that?
See, there are three types of calibration which is being used, presently globally. One is a normal external calibration. That is a pure standard calibration. Another calibration being used is a matrix match calibration. That means you extract the matrix, and using that matrix solvent, which is the final extract, we prepare the standard. And another one is matrix based calibration or procedural calibration, which is presently being used. So in case of procedural calibration or matrix based calibration, there is no dilution factor coming at all. However, in case of a matrix match calibration or an external calibration, automatically the dilution comes into picture. It may be multiple dilution within the method, or maybe it may be a single dilution within the method. So you need to take that into consideration. See, the problem what is happening when it comes to band compounds is when we try to do pure standard calibration, the accuracy of the quantified results may not be more precise. You can have accuracy in the method, but then you should have an internal standard being used, mainly in band compounds. If you are using an internal standard, along with that, if you ensure that there is no matrix effect. So ideally, if you ask me for your question, the ideal answer is you need to study matrix effect. And matrix effect is comparing pure standard response against a matrix match. So you can use a area as a indicator, or your slope, y is equal to mx plus c, your slope as the indicator, and any effect more than plus or minus 20% is considered as matrix effect. It can be negative, minus, or it can be plus, positive, or signal suppression or signal enhancement.
Thank you, sir.
Yeah, thank you for this information, sir. Any further questions or any queries? You can just type in the chat box. We have some 1 or 2 minutes left. So quickly, if any questions, sir can answer.
Yes. Please tell me about SPE system, sir, solid phase extraction system, and where it is required.
See, there are, let me tell you, see, mainly in solid phase extraction, which was just before where dispersive SPEs came into picture. Now, solid phase extraction is like this. We have a extraction which is being presently given by many of the OEMs, where in which the actual target analyte will be trapped on the phase, okay, on the solid phase, which is generally proprietary in nature. And once it is trapped, all the other impurities are being removed off through the solid phase extraction. And through the final cleanup, you will actually target the actual analyte. Now, solid phase extractions are being vastly used when people were doing analysis for tetracycline sulfonamides. Now, what has happened is we moved from solid phase extraction to dispersive SPEs. That means ready-made packets. Like Quetcher's method, it is something like you use dispersive SPE, Quetcher packages like magnesium sulfate, sodium chloride, or C18, GCB, or like this. Chemicals are coming in ready packs, and these are dispersive SPEs which are being used for cleanup. However, still SPEs are being used in many places where fat content is very more. When fat is more, people still use SPE cartridges. These are cartridges which are pre-packed with some sorbent, and these sorbents target only the analyte, and the other impurities are being removed. So that is how you need to elute the actual target analyte.
Okay, thank you, sir.
Okay. Thank you, sir. Thank you so much for such an informative session. And then we really got a lot of very recent information from your talk, and we really humbled to you have here in this today's our training program. So thank you so much, sir.
Thank you so much. Thank you, Dr.
Yeah. Fine. So in continuation, going further in our today's training program, we have another lecture. and talk. Visible. Yeah, so in the series of the further lecture, so like we have Dr. Manish Gada sir, who is a service executive in LCMS Waters India Private Limited in the regional office of Mumbai. So sir is going to talk on the topic, the basics of the LCMS troubleshooting, the tools, cases and strategy. So sir will talk on this particular topic. Before that, I would like to just briefly introduce Dr. Manish Gada sir. Dr. Manish Gada sir is actually did his B in instrumentation in 1998 from the Mumbai University, and afterward for more than 20 years, and he is serving to different organizations. Currently, he is working with Waters India Private Limited, regional office at Mumbai. So herewith, I would like to request and ask Dr. Manish Gada sir to please begin with his talk in lecture. Manish Gada sir, please.
Yeah, thank you. Thank you very much. First of all, thank you very much for giving me opportunity to speak to this huge audience, huge participants who are more knowledgeable probably than me in this field. I'll be talking in general the troubleshooting for the LCMS equipment. It will be a generalized talk. Whenever anyone feels that they have a question, they can either write it in the chat box, or you can raise a hand, or you can directly ask over here. Can that be done? Can they ask directly the questions over here? Okay. So whenever they feel, they can interrupt and they can ask the questions. So we need not wait till the end. So I have not kept a special session for question and answers. You can just interrupt at any point of time, and you can just ask the questions. This topic may not be in direct connections with all the users right now, all the participants over here. This will be more useful for the persons who are actually using the instrument. So of course, others may gain some knowledge when they are ready to use the instruments. So they have the first-hand information what we are discussing over here, right? So we start the presentation over here. The agenda of understanding the LCMS flow path, the operational tips when you're trying to use the instrument, what precautions and what tips can help you in getting the better results, the troubleshooting steps, understanding the common LCMS problems and causes and how to overcome them, understanding the chromatography or basic LC related problems, most commonly the peak shape issues, the overpressures, then the contaminations, and finally the LC cleaning protocols, what we can do regularly to clean the LC part, then the MS troubleshooting, and finally the startup and shutdown, how we can start up the instrument and how we can shut down the instrument. So starting with the LCMS flow path, this is a typical LCMS. This is actually from Waters. You can have any other vendor, but probably they will have the same flow path. That is, you have the mobile phase. The mobile phase will be drawn to the sample manager, and it will be pushed towards the sample manager. The sample manager will assist in introducing the sample along with the mobile phase onto the column and the column heater, which is the column is residing in the column heater, and the outlet of this column will be going to your LCMS detector. You can have an optional detectors over here, but presently we'll be discussing more on the MS detectors. The operational tips when you are performing the LCMS experiments, you can follow these steps to have minimum breakdowns and get optimum results. Starting with the gases. Before starting the instrument, ensure gases are set at the specified settings. Like for this, operating LCMS instruments, we have certain gases required, like argon and nitrogen. So before starting the instrument, ensure every time while performing any experiment, ensure those gases are present and they are set at the specified settings. Deviating from those settings can largely hamper your results. So ensure those settings are correct. Then going to the mobile phase and the solvents. Use proper solvents. We generally recommend LCMS MS grade solvents to have minimum contaminants, so they don't interfere with your results. And if milky water is there, then the proper maintained milky system should be there. Only then you can use that milky water. Keep dedicated glassware for LCMS systems. Do not use the generalized glasswares. The glasswares which are used for preparation or extraction or the mobile phase should be kept separate for LCMS systems. Always prepare fresh mobile phase and diluents whenever you want to perform any experiments. It is recommended that you every time prepare a fresh mobile phase and the diluents. Never use the previously stored mobile phase, because that can degrade and affect your results. Okay, because most of the time we will be adding some additives in that mobile phase. So over a period, that additives may degrade and affect the results. So it is always recommended that you prepare a fresh mobile phase and a fresh diluents. And also, if water is kept for a longer time, there will be a microbial growth. It is seen that over a period of 4 hours, the microbial growth starts in water. So we don't recommend to store water or aqueous mobile phases for longer time, right? So whenever you want to perform any experiments and if you have aqueous mobile phase, better to prepare the fresh mobile phase every time and discard the older one. So whenever you feel that you want to prepare mobile phase, prepare mobile phase only the quantity which is required to run the experiment. Okay, don't, I mean, if 500 ml is required to run the total experiment, don't prepare 2 liters or so, thinking that I'll run the same mobile phase tomorrow again or the day after tomorrow again. So that can hamper your performance. Use proper combinations of solvents for needle wash, especially this is for your sample manager or the auto samplers. Wherever you need to wash the needles after injection, the proper solvents has to be placed to wash the needle after every injection. Never use paraffins to cover the solvent bottles. And clean the mobile phase filters periodically. If you have seen the solvent bottles, there are some filters connected to that lines. Okay, so they're easily removable. Over a period, they will be partially blocked. So what we recommend is periodically, probably once in a 15 days or so, we remove that and clean it in suitable solvents. Depend on what mobile phase you are using. If it is aqueous, better to use methanol and water combination first, and then with methanol. Then the next part will be your solvent managers or the pumps. which are pumping the mobile phase to your further parts, to the columns. So when the precaution or the operational tip related to the solvent manager is, whenever you are performing any experiment, better to prime the mobile phase lines properly with the required solvents. Whenever you are putting some new mobile phase in particular line, ensure that proper priming or proper flushing of that line has been done with the required mobile phase. Never keep aqueous mobile phase in unused lines. Say there is a quaternary solvent manager which has 4 solvents and you are using only 2 of them and 2 are not used. So never keep aqueous mobile phase in unused lines. Then the column and column heaters. Ensure proper tubings and fittings are used for columns and in other places. That will see what an improper fitting can lead to in further slides. But remember, whenever you're disconnecting and connecting the columns, you make a proper fitting for the tubings and the columns with the proper nuts and ferrules. Equilibrate columns with mobile phase before starting the analysis. Normally we say that at least 5 column volumes has to be passed through the column before starting any injections. Do not maintain column at higher temperature without flow. So before starting or at the end, when your experiment is completed, ensure that your column temperature is lowered before stopping the flow, mobile phase flow. After the analysis is completed, flush the column with water and then organic solvent, or as suggested as per the manufacturer. But in general, what we say is flush the column with water to remove all the additives and then finally store the column in organic solvents. Again, as what we say is always store columns in organic solvents, or again as suggested by the manufacturer. Then the sample manager. Use standard vials with pre-slit septa caps. Never interchange those caps with the without the pre-slit septas, and always use the standard vials. That is, different vials have different lengths and different IDs. So use the proper that is recommended from that manufacturer. Set sufficient time for washing sample needle after injection. Like after injection, we need to wash the sample needle, and sufficient time or a sufficient volume has to be pumped to clean up that needle, or that contamination or that carryover will be reflected in the next injection. The MS detector part. Set proper mode of operation in method. Suppose if you want to run an MS experiment and you are set as a MS experiment, then that will not give a proper result. And the entire experiment has to be repeated. So to avoid that, set proper mode of operation in method before starting any experiment. Ensure proper tune parameters are set related to that method. If you want to run a particular sample, that method has to be in place. If you use some other method by mistake, again your experiment has to be repeated. That may not give the proper results. And before starting any analysis, ensure proper spray is present in your source region. You can visually see the spray. So ensure that you get the proper spray over there, ensuring that your column flow is going to the MS part. Right? So that was the operational tips which you can take care of before starting any experiment to avoid any failures. Now the troubleshooting part. When things go wrong, troubleshooting can be a complex task that requires proper understanding of the instrument or the system, complete system. The system also involves, like the previous lecture, the sir told that your sample preparation is also part of your system. So complete understanding of your system is very important in troubleshooting if anything goes wrong. Extracting the relevant information from what has gone wrong, and then logically making some decisions to have a corrective actions. Usually there will be a mass of information or huge chunk of information available for troubleshooting, but not everything is relevant. Accurately defining the symptoms enables concise filtering of relevant information. Right? So when you're facing certain problem, try to dig out and have a relevant information. Like, for example, if you're facing a problem with flow, pump flow, and if you're working at MS part, so that information is wrong. You need to precisely work on the solvent manager when you have a problem related to solvent manager, or there is a flow related issue. Okay, so pinpointing at particular problem and the symptoms is required when you do any troubleshooting activity. The strategy that you can follow is, how do you isolate the cause? Gather the facts. Like example, talk to the last user who has done the last experiment. Look at the last data. You can find out certain information from that. For example, there is a flow related issue. Then you can monitor the pressure during the last experiment that was run. From that experiment, when the problem started, what was the experiment running at that point of time, you can make some inferences from that, and then you can start the troubleshooting part. So it is better to grab some instrument related facts or the basic understanding of that problem. Check the simple things first. Instead of jumping to the complex instrument related problems, start from the basics things and the simple things which are easier to do. Compare the system performance against the established benchmarks. Like the same sample, same standard was run previously, and that gave correct results, and now it is giving some weird results. Then you can compare what has gone wrong. If it is suppose there is 10 peaks in my analysis and only one is going bad, so is it related to the complete sample, or is it related to that particular analyte? So try to compare the results with the previously set benchmarks. Isolate the root cause, the process of elimination. You start eliminating one by one and coming to the cause of problem. Resolve the problem by performing recommended actions. Like there are some recommended actions, like you need to flush the system properly. Test the solution to make sure the problem is solved. Like once you come to some judgment that this can solve my problem, then actually run that sample and ensure that it has been solved to the totality. And once that is done, educate others to avoid the problem in the future. So troubleshooting some common issues. Then there are some lists of problems and how to overcome those problems. This I will not go through each part, but I will share this to some persons and they can share it internally. But yes, some common problems which are faced that we can go in detail of that. This is some list of those problems. So now troubleshooting the chromatography part, all the LC part initially. Top 4 things that can introduce chromatography issues. This should be addressed first before attacking the hardware. Mobile phase, column, sample, and manual errors. If you have some problem and you want to troubleshoot, before jumping onto the hardware, it is better to check these things first, because most of the cases we have found out these are the primary cause of problem. Forget about hardware issues are separate, but some operational issues, like if your mobile phase is not correct, you can change the mobile phase and check it again. Your column is showing high back pressure, so you can remove the column and connect another column to ensure that the high pressure that is shown is related to that column or it is from the system. It could be a sample issue, so ensure working of the system with some other sample which was previously run. And there could be some manual errors, like instead of placing one mobile phase, you have placed some other mobile phase and you're trying to run the experiment. So that could be manual errors, and we are humans, we can make those mistakes. So ensure that we are not doing any errors by eliminating these probable causes. If these are eliminated, then we can ensure that there are some actual hardware issues, and then we can try to figure out what hardware issues can be solved. So now the basics and the frequently occurring chromatography problems. First is peak shapes. The frequently occurring we see is there are bad peak shapes occurring frequently. The 3 major peak shape issues are the peak broadening, peak tailing, or peak fronting. And we'll see in detail what could be the reason and how can we troubleshoot those issues. First is a peak broadening. So if you see, there is a comparison of a good chromatogram and a bad chromatogram. The bottom one has a peak broadening issue wherein the resolution of each peak has not gone to the base. Okay. So this can be a common problem. Peak broadening occurs when the dispersion or the band spread of the system is higher than expected. The peak which is eluting out from the column is not coming as a narrow band, it is spreading out in the column. So what could be the reason? Things to check: the system configuration, anything has changed in the system as compared to the previous experiment, you can check that. Is the column reason for that broadening? Or if there is a preheater connected for the column, is that functioning properly? Yes, there could be some other issues also, but these are the common issues what we understand. Like if your preheater is there, and if that preheater is not configured properly or you're not working properly, then that could lead to this problem. There could be certain peak that is not eluting properly. That requires preheating before it enters to the column. So if that is not done, then it can have those issues. Like the next example, only one peak, it is getting merged with some other peak. Okay. Yes. Yes. Again, the solution itself is written on there. When you are changing the column, the tubings which you are connecting to the column can also be a part which can contribute to this sort of problems. If there can be a dead volume in the column fitting, that could lead to this type of problem wherein only one peak gets affected. I mean, two peaks are there, but that is getting merged. So that shows that it is not is separating out properly. So that could be a reason of the tubing connections or the column connections for which your tubings and fittings you are using. We'll see how that can be eliminated. Check for voids or improperly seated ferrules. Check for leaks. Normally, before going to the next one, what question you asked was how can you check or how can you ensure that? So whenever you are connecting any column, normally you are using peak tubings, right? And the peak ferrules to connect the columns. So ideal condition would be whenever you want to connect the column, you uh, completely insert the tubing inside the column till it touches to the bottom, and then go on tightening the ferrule. That ensures that there will be no void inside the column. Suppose if you are not flush the tubing completely to the bottom of the column and there is some gap in between, and you just tighten the ferrule over there, so that there will be some void in between. So all your sample will be collected in that part, and slowly in, uh, it will be going into the column, and that could lead to tailing or merging of the peaks. Gradient, yes, it will affect. It will affect all the peak shapes. No, this is irrespective of the flow. Before starting any flow, whenever you want to connect any column, ensure that the tubing is flushed or it is touching the column bottom. Wherever the fitting goes, it touches properly, and then you tighten the ferrule. Then irrespective of whatever flow you are giving, you are ensuring that there is no void in between. And another part to that is you connect the fittings or the nuts which are recommended for that column. Every column or most of the suppliers will have different geometries inside the fitting. So proper fittings are necessary to ensure no voids are left out. Because some columns may require longer nuts and ferrules, some may require shorter ones. So if you uh, connect the other ones, there are chances that you will get a void. Sure. Yeah, the question is which organic solvent can be used to store the columns? Generally, yes. Generally, what we recommend is what normally we do is we either use acetonitrile or methanol to store the column. Again, that depends on the manufacturer what has been suggested in their COA. But if nothing is mentioned, then acetonitrile or methanol is good enough to store. Yeah, can be done. Is that clear? The question. Okay, fine. We continue. Next, related to peak shape is peak tailing. If you compare the lower one, that in that the sensitivity has come down, and you can see the peak broadening and tailing, more prominent peak tailing towards the end of the peak. So there is some explanation. Peak tailing can occur when the sample is held up during the injection to the point that it doesn't all separate at the same time, indicating there is a tailing in the peak shape. It is similar to peak broadening. The reason what could be the probable causes is the preheater settings and the voids in the fittings. You can eliminate that, and probably you can eliminate the tailing issues. Yes, that is there in the next slide. Yes. Yes, it is not eluting properly, and there is a band broadening, so that can lead to this tailing issues. So this is what we are talking about. So this is the column, and the purple one is your tubing, and these are the nut and ferrule which you connect to the column. So when the nut and ferrule are sitting outside the fitting, the column fitting, there will be some gaps. So that can lead to leakages. Okay. If it is not, the tubing is not touching the column part over here, this part, so there is a void created in between. The sample can reside over here for longer time, and that can lead to your broadening. Okay. The ideal situation would be the tubing will be touching the column properly, and then you tighten the nut and ferrule. Right? But physically you cannot see these fittings. So to ensure that your fittings are proper, you just push the tubing first inside the column, and ensure it touches the column end properly, and then tighten the nut and ferrule. Okay. So you are making sure there is no gap in between when you are tightening the nut and ferrule. Right? So again, this is one part of tailing, wherein all the fittings and everything is correct. The explanation what it has given over here, the chromatogram on the left shows a comparison of a same high molecular weight component passing through a taper slit SS flow cell versus a light guided flow cell. This is a light guided flow cell which is giving a tailing, and there is different type of flow cell which is not giving any tailing. So it could be the material. Sometimes some specific compounds react to the internal tubing material. So sometimes they get trapped onto those material and they elute out slowly. So some compounds are material specific. So you need to use those specific materials to perform the experiments on those molecules. Right? There is nothing wrong with this system, only the component is so specific that it requires some specific material to perform those analysis. Now, the peak fronting, another common issue. Peak fronting occurs when a percentage of sample is jump started through the column before it is expected to elute. There is some pre-injection happening that could lead to fronting. Things to check is, again, the preheater is working properly. Another reason could be strong solvent defect. Strong solvent defect is when the amount of organic solvent injected from the sample diluent is too concentrated when compared to the initial mobile phase conditions. When your diluent has more organic as compared to your mobile phase starting conditions. At that time, you can see such the red chromatogram. It shows some peak fronting. This could be a reason when your diluent is not matching to your initial mobile phase conditions. So when you're developing any method, we suggest that you try to match the diluent, the final diluent in which your samples are prepared. You try to match it with the initial mobile phase conditions. When you're running some gradient, so the initial gradient conditions and the diluent should match or should be as close as possible to avoid. If it is matching, it is better. Or you may have to compromise in certain parts of your analysis. Every peak may not show this type of problem, but if you're okay with that, you can continue with this. It is recommended, but if you are not able to go through with that, the same conditions, then you need to compromise with certain parts. Suppose if this initial peak of interest is not peak is not of interesting to you, then you can continue with that, right? Again, the peak fronting, this is what we are talking about, the injection volumes. If your injection volume itself is quite high, then that could also lead to this peak fronting or peak broadening issues. So try to inject the lower ones and ensure, try to get the proper peak shape if that is helping out. Early or late eluting peaks. Start with some configuration. Is anything changed in that configuration? Have you connected some longer tubing or some shorter tubing? That could also lead to this early or late eluting peaks. What's the column temperature? is the column temperature working properly? If your analysis is supposed to be performed at 40 degrees and you are set at 35 degrees, so that could lead to the late eluting peaks. So is that working properly? Try to eliminate that. There is no optimum as such. There is no thumb rule as such. Whatever separation you are interested in and whatever temperature at that temperature, if you are getting that separation, that is the optimum temperature. There is no thumb rule as such what temperature has to be set. Could be. That could be one of the reason. One reason could be this next point over here. For the gradients, is the re-equilibration time long enough? The re-equilibration step should be similar to the starting point. That is, when this is the actual analysis time and this is the re-equilibration time. So the column has to re-equilibrate to back to the original step, and that time should be sufficient enough so that the next injection is working properly. Should be same, and sufficient time has to elapse to start the next injection. Again, that timing is again not fixed. Generally, we say normally 3 to 5 column volumes is good enough to have a re-equilibration timing. Early eluting peaks are a symptom of over delivery of organic or under delivery of aqueous solvents. If your peaks are eluting early than expected, then it could be organic is going more into the column. That could lead to early eluting peaks. Right? Exactly. So it is better to sort of maintaining a logbook, like whenever you are starting an experiment, what could be the starting pressure? No, no, we are not talking of delta. Delta is definitely important to run your analysis, but before starting that, going to that delta, you monitor. Say, suppose today I'm working with some experiment and that is giving us 9,000 starting pressure. Tomorrow it has gone to 9,500 or it has gone to 8,500. So there is some change in that initial pressure. So that indicates there is some change in the system. So I need to address that before starting the experiment. The sources of overpressure can be particulates in your mobile phase. How to overcome that? Use good quality solvents that need not be filtered. Again, good quality mobile phase additives, undissolved particulates in your sample. Always visually inspect your sample for undissolved particles or cloudy appearances. Whenever possible, filter the sample. Alternatively, centrifuge your sample and take out the top part of your sample. If precipitation is suspected in your vial, change the needle depth. So needle should not be allowed to go to the bottom part of your vial, as your bottom part will be containing all the precipitations. Ideally, there is 4 mm from the bottom of the vial. If you observe some precipitation and you cannot help it, then you need to change it to some higher values. Ideally, that should not be injected. You're testing the instrument. Okay. Switching between applications, when you are changing some application, changing your mobile phases allows sufficient wash up of old mobile phases before running the new mobile phase. Like there are some buffers that were run in the previous experiments, and you are changing the method now. So it is better to remove all those previous buffers with water and then connect the new mobile phase. Sources of overpressure can be again column. Always filter samples. Better idea to have a pre-filter or a guard column onto your analytical column. So that will ensure your column life is extended. Flush the LC system with water and high organic to remove buffer components. Clean and store your analytical column with high organic at the end of each batch. Use sample diluents that are miscible with the mobile phases. Instrument contamination can build up in mobile phase, LC, injector. These are all the places where you can have the contamination. How does it reveal itself? In mobile phase, if you have the contamination in mobile phase, you have blank peaks or the broader and elevated baselines. If it is in LC, it could lead to carryover. If it is in tubings, it could lead to higher baselines and decrease in sensitivity. The columns can also lead to baseline issues and sensitivity issues. If it is in MS, this could be the places where it can have the contamination issues and what could be the effects of that contamination. And how to troubleshoot those contaminations. Okay. So more so it is related to your mobile phase and the samples which needs to be taken care of. This could be some contaminations, examples of contaminations. Even in your blanks, you see some peaks. So this is an example of your contaminated mobile phase or the contaminated diluents. Again, some examples related to your contaminated mobile phase. So this is not only the mobile phase, but the bottles in which those mobile phase are taken could be contaminated. So this is an example of that. It is the initial mobile phase, the new mobile phase in the same bottle, and new mobile phase in new bottles. So that's why initially when we were talking, we suggested that the glassware which is used for LCMS system should be separate, should not be used for as a general glassware. Again, some example of your contamination which gives rise to your elevated baselines and lower sensitivity. This is the one contaminated. This is the one after the contamination is removed. You can see the baseline is correct over here and the sensitivity has improved. So there are some LC cleaning protocols which you can follow. In this LC protocols, whenever you are following these cleaning protocols, the important thing to follow is you should not allow the LC flow to go to MS part. You are performing only LC cleaning part. Okay, so whatever is coming out from LC should not go to your MS. There is a magic solution or magic mix wash one way, and the other way is the phosphoric acid cleaning. I'll tell it is there in the next slide. This is a magic mix wash which has 25% each of water, ACN, methanol, and IPA with 0.2% formic acid. Remove the column, connect the union, and set the MS diverted to waste. And set the flow to 0.2 ml per minute and allow it to run overnight. And this could be all the mobile phase lines. A, B, C, and D. Everything should be put in this bottle and everyone should be pumping for a longer duration of time. And once that is done, properly flush the system with water and then methanol, and finally then you connect your mobile phase. As IPA will take longer time to remove from the system. This is one way of controlling your contamination. I mean, cleaning up your contamination. If this is not helping out, then there is a stronger acid wash. That is, you use the phosphoric acid, but this is not recommended to be used in a general purpose cleaning. Only when you are not able to remove the contamination by trying out all the methods, then this is a final source of troubleshooting, wherein you use 30% phosphoric acid and wash all the lines using this type of gradient. And again, the care has to be taken. Your column is bypassed. You connect the union in between, and the outlet should not be allowed to go to MS. Since again, this after this wash, phosphoric acid will be difficult to remove. So proper water washing is required after you complete this step. Probably you need hours and hours to remove phosphoric acid. Right? So that was related to your chromatography or LC part. Now your troubleshooting related to MS. I'll not go in detail about this MS because generally you will not be able to, I mean, you need not change certain things in this. So like the calibration files, if the improper calibration files are used, then there will be some shift in your masses. This is a correct calibration file applied, wherein you have the center mass at the apex. If the calibration file goes wrong, some previous calibration file has been applied, so your center mass and the um, the embase rate that is you are using for your method are different. So there is some shift in your masses. So that is not the optimum sensitivity what you need. So initially you are getting some sensitivity over here. You will have some decreased sensitivity in this case. So whatever calibration you are using or you are applying in your instrument should be the current calibration file that is performed. Okay. Now the analyzer settings, there are high mass and low mass resolution settings in your instrument. If those settings are not correct, that could also lead to your sensitivity problems. Like this one, if your resolutions, this is the optimum resolution that is expected, and some resolution changes in this. If you see, there are some changes in these values. So those values are not correct. So if those values are not correct, you can get some decreased sensitivity issue. So whenever your calibration has been performed, you get some resolution values. Those resolution values has to be put in your method. Same way, your ion energy, when your ion energy values are not optimum, that could lead to your sensitivity issues. The ion energy which was supposed to be there is not there and it is low, then that could lead to lower sensitivity. Or if it is too high, that could lead to peak shape issues. So sometimes you get the apex over here, sometimes you get the apex at some other part. So there could be some issue related to your reproducibility if your ion energies are very high. Now, whatever values you get in the calibration, you need to put that in your method. So suppose this value was obtained in your calibration, last calibration. So you need to put in that value. Right? The MS contamination, as in the morning session, we see that only the mass of interest is allowed to pass through your quadruples, and the rest of the masses will collide or go away in that quadruple region. So where that quadruples go, it will be sticking on to this quadruple parts. Over a period, this could be the effect. You can see some contamination in this quadruple region. Again, you cannot do anything, but you can understand there is a contamination. You need to call some technical person to take care of that. Right? Same way with your source and analyzer part of MS, over a period, some unwanted things will deposit on those parts, and you require a cleaning, periodic maintenance of those parts. Like you normally clean the cone, right? But still there are some unwanted things that are going inside and that are sticking onto the various parts of the instrument. That has to be cleaned periodically, or that could lead to sensitivity issues. There is again no thumb rule, depends on your usage, your type of analysis, and the mobile phase that you are using. But yes, at least once in a week is good enough to clean that. Right? So we come to the last part of this, the start and the end of the sequence. Before starting any sequence, prime the system properly, allow sufficient time for the MS to stabilize, equilibrate the LCMS system with organic solvents, load onto the initial conditions, perform a no injection and a blank, perform a QC check to ensure your system response is optimum, and then run the sequence. Common thing is the contamination. Her question is, the QC is performed, say, in interval in a sequence. After, say, every 10 injections, they are performing a QC. And the QC response is going down over a period. So we are facing a sensitivity issue, decrease of sensitivity. The primary reason for that could be a contamination. It could be the contamination of MS, it could be the contamination of column, or it could be any contamination of even the mobile phase. So just that's why we are talking, like, before you do any experiments, you perform these startup things and you follow some tips that we were discussed in the start, so that we ensure the starting points are correct. Later on, still if there is some problem, then we need to troubleshoot that. But we can eliminate certain things by doing this proper startup and sticking with certain operating procedures. Right? Again, after your analysis is complete, how to do the system shutdown? Allow both LC and MS to be flushed with high organic solvents to remove out all the buffers. Decide whether to put the MS in standby. Again, you want to run some samples, or you want to completely stop the system. Only then you put the system to standby. Decide whether to stop the LC flow. Again, if you need to run the samples, some other batch has to be run. You need not shut down the flow. You can continue the flow so as to minimize the equilibration time. Okay. Again, this depends on how long the system will not be used and on personal preferences. Okay. So that is the end of this presentation. Again, if you have any questions, you can ask, because I have taken some extra time.
It's fine. So really we are, very much thankful for such an interactive session. Still, if any further questions or queries, you can.
Nothing, no logic as such. Only thing is, you need there is some general practice, like whenever you are developing a method, you keep A as a aqueous one, B as a organic. That is a general practice. There's no thumb rule again. Like you don't forget some by mistake if you have kept aqueous in B and organic in A. So there is a change in gradient. Yes. That is what, whenever you're changing such type of things, you need to flush the system properly. So all the organic is removed out from the aqueous line and system is stabilized properly. Yes. 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 So you can see that over a period of time, say 3, 4, or 4 injections, it will start stabilizing. So that is not flushed out properly. So generally, if you're using A as a aqueous one, you try to maintain A as a aqueous one. Only thing is, periodically you need to flush it with organic to maintain there is no microbial growth in aqueous lines. Right?
Yeah, so really it's a very interactive and then a very exciting session, sir. And then we are very much thankful to you for such a elaborative explanations of the basic troubleshooting problems in LCMS and LCMS. So we are really thankful for your such a nice presentation, sir.
Yeah. Thank you, everyone.
Fine. So in today's session, on the day 1 of our 2 days online training program on antimicrobial residue analysis in chicken meat by the liquid chromatography, tandem mass spectrophotometry. So we came to an end for the first day, all the topics delivered by the various eminent speakers from the various fields. And on behalf of the MAPSU, all the officials and then the university authorities and Naib Caste Office, ICAR, all the officials from those, we are very much grateful and then thankful to them that they have given this opportunity to schedule this 2 days training program. And then we are very much thankful to all of them. We also thankful to the associate dean, the PI of the project, all the co-PIs, and all the aspiring team of this Naib Caste project for making a success of this 2 days training program at the conclude of the day 1. Again, we will be meeting tomorrow again for the tomorrow session. But before going for tomorrow sessions, as today we are getting an opportunity, herewith we would like to, as a token of our love and affections and appreciation, we would like to give a small gift to Dr. Manish Gada sir. Thank you so much, sir. Thank you so much. And then I would like to invite and then request Dr. Manish Salunke sir also to accept, Nishant Salunke sir also to accept our token of small love and appreciation from Bombay Veterinary College. Thank you. Thank you so much, all the participants. And herewith, we would like to conclude the today's session. And again, tomorrow we will meet up as per the scheduled time for our day 2 of